Right, so integration by parts. You know about integration by substitutions, that the reverse of chain rule differentiations. Right? Integrations by substitutions, reverse of chain rule of differentiations. For integration by parts, is the reverse of the product rule of differentiations. So for the product rule, if you want to find the derivative of two functions that is multiplied together, is equal to f prime of x times g of x plus f of x times g prime of x. So instead of using prime for the left hand side, I'm going to write d dx just for the purpose that I'm going to use in the next step. But it's the same meaning, right? You prime or you use d dx. It's to indicate that you want to take the derivative of the product. As the right hand side remain the same. Right, so from this product rule, you're going to integrate both sides of these equations. Right, so you integrate d dx of f of x times g of x, and you integrate both sides with respect to x. That's what you get. So x integral of f prime of x times g of x dx plus the integral of f of x times g prime of x dx. You start out with the product rule of the differentiations, then you integrate both sides of the equation with respect to x. The left hand side, you use fundamental theorem of calculus part 1, and you get just f of x times g of x. And the right hand side remains the same. So to obtain the formula for integration by parts, I'm going to rearrange this equation a little bit. So I have f of x times g of x minus the integral of f prime of x times g of x dx equal to the integral of f of x times g prime of x dx. Then I'm gonna let u equal to f of x. Then I have du equal to f prime of x dx, and v equal to g of x. Then dv is equal to g prime of x dx. So instead of writing f of x and g of x, I'm going to use u and v. So u is equal to f and v is equal to g. So I have u times v minus the integral of f prime dx is equal to du, and g of x is equal to v. So v du equal to the integral of, so f of x is equal to u, and g prime of x dx is equal to dv. So that is the formula for integration by parts. So for integration by parts, you have the integral of u dv is equal to uv minus the integral of v du. Let's talk about the choice of u, because you cannot just randomly choose u, right? Because you just randomly choose u, then this might not work out for you the way you want. So the choice of u should follow ilate or liate functions. All right, so I, L, A, T, E. All of this are the abbreviations of some functions that you have seen before. Let me start out with I. You know that you see this type of function before. So I is for inverse trigonometry functions. What about L? Logarithmic function. What about A? What about T? And what about E? E is for exponential functions. What about A and T? Trigonometric. For T, what about A? Algebraic function. You should follow this for the choice of u. It's ranking from top to bottom, right? So if you see inverse trigonometry functions and logarithm, or let's say exponential function in the integrand, you should choose u to be inverse trigonometry function. Right? Follow that. Why is I late and liat? Because most of the time these two functions can interchange, can be interchanged. Then everything else will follow the ranking from top to bottom, with the exceptions for trigonometric function and exponential functions. There's the case that you can switch between exponential function and trigonometric functions, but that's for later. For now, follow this ILATE or LIAT functions. So let's take a look at some of the example. So you would like to evaluate the integral of x e to the x dx. So you have two functions that multiply together in this particular integral. One is x, the other one is e to the x. Right? So x is the algebraic functions and e to the x is the exponential functions. So x is the algebraic and e to the x is the exponential function. When you go back to the liat or ILATE, you will see that algebraic function has the higher rank. So you let u equal to x. And from here, you have du equal to dx. Right? You let u equal to x, you differentiate that, you have du equal to dx. And what I'm going to do is I'm going to let something called dv equal to the remaining terms inside the integral, which is e to the x dx. You kind of find the antiderivative. Right? So the antiderivative of e to the x is e to the x. Right, and then you apply the integration by parts formula. Right, so u times v minus the integral of v du. Right, so u times v minus the integral of v du. That's what you got for the formula. Right, so the integral becomes u times v, which is x times e to the x, minus the integral of v du, which is e to the x dx. Right, so x e to the x remain the same. The integral of e to the x is e to the x, and then you plus the constant c because this is the indefinite integral. As I mentioned, you should follow this ILATE functions. Look at the rank. Right? If you choose u equal to e to the x, you're not going to be able to solve this problem at all. Right? It's not going to work out. If you want, you can try it out. But you should not be able to solve this integral by letting u equal to e to the x first. Alright, let's move on to the next example. Want to evaluate the integral of x times cosine of x dx. You see that x is the algebraic function and cosine of x is the trigonometric function. Right, so follow the ILATE. You see that the algebraic function has the higher rank than the cosine of x functions. So you let u equal to x, and therefore du is equal to dx. And dv equal to cosine of x dx. Right, so dv is the remaining terms in the integral. And for this step, you find the antiderivative. The antiderivative of cosine of x should be sine of x. And you apply the integration by parts formula, u times v minus the integral of v du. You get, so u times v is x times sine of x minus the integral of v du, which is sine of x dx. And the integral of sine of x is negative cosine of x plus a constant c. You simplify this. You have x times sine of x plus cosine of x plus a constant c. So evaluate the integral x squared times ln of x. For this particular example, you have x and ln of x involved in this, but if you remember, we briefly talked about the relation between ln of x and 1 over x. When that's the case, you should use integration by substitution. But there's no 1 over x in this case, so there's a good chance you should use the integration by parts. Right? So once again, you look at the functions inside the integral. You have x squared is the algebraic functions, and ln of x is the logarithmic functions. So for the ILATE abbreviations, you see that logarithmic function has a higher rank than algebraic functions. So you let u equal to ln of x, or du is equal to 1 over x dx, and dv is equal to x squared dx, or v is equal to 1/3 x cubed, because we're trying to find the entire derivative of x squared. Once again, the integration by part formula is uv minus the integral of v du. You get this is 1/3 x cubed times ln of x minus the integral of 1 over x times 1/3 x cubed dx. Right, so you can simplify the integral. 1/3 times the integral of x squared dx. And so entire derivative of x squared is 1 over 3 x cubed. So 1 over 3 times 1 over 3 x cubed plus a constant c, and therefore the answer is 1 over 3 x cubed ln of x minus 1 over 9 x cubed plus a constant c. The next example, evaluate this integral of ln of x dx. So you only have ln of x in this case. Compared to the previous example, you have x squared ln of x. If you look at this function, you just have ln of x. But instead, if you notice this is 1 times ln of x. Is equal to ln of x. So 1 is the algebraic functions, right? And ln of x is the logarithmic functions. So you let u equal to ln of x, and so therefore du is 1 over x dx. The remaining term is dv equal to 1 dx. So v is equal to x. So you get u times v, which is x ln of x, minus the integral of x times 1 over x dx, equal to x ln of x minus the integral of dx, or 1 dx. Get x ln of x minus x plus a constant c. So for the next example, this example is for repeated use of integration by parts. So sometimes you have to do integration by part twice. So you evaluate this integral. So x squared times sine of x. So once again, x squared is the algebraic functions, and sine of x is the trigonometry functions. Algebraic functions has a higher rank than trigonometry functions. So you let u equal to x squared, and therefore du is equal to 2x dx, and dv is equal to sine of x dx, or v is equal to negative cosine of x. So the formula applied here, and you get negative x squared cosine of x minus the integral of negative cosine of x times 2x dx, and pull the negative 2 out of the integral. You get negative x squared times cosine of x plus 2 times x cosine of x dx. So at this step, you see the integral. This is a product of x and cosine of x, right? So once again, x is the algebraic functions, and cosine is the trigonometry functions, right? So you have to do another integration by parts in this case, right? So this is the second time we use integration by part for this problem, right? So you let u equal to x, and du equal to dx. Dv equal to cosine of x dx, or v is equal to sine of x. So you have negative x squared cosine of x, so I just copy the first term here. And for the second term is the integral And we just use the integration by parts to evaluate that. You have 2 still outside, multiply with u times v, which is x times sine of x, minus the integral of sine of x dx. So you have negative x squared times cosine of x plus 2 times x times sine of x minus 2 times the integral of sine of x dx. And the antiderivative of sine of x dx is negative cosine of x. Plus the constant c. And for the final answer, that's what you get. For integration by parts, you can do multiple integration by part for one problem. And you need repeated use of integration by parts to get the answer. And there's also a situation between if you have a product of exponential function and sine and cosine function, you have to do integration by parts twice to get the answer. The next example here, evaluate the integral of e to the x times cosine of x dx. So for this one, you have a product of exponential function in a way of trigonometry functions. You can let u equal to either one, right? This is the special case. You have to do integration by part twice, this particular problem. If you let u equal to the exponential function, the second time you do integration by parts, you also have to let u equal to e to the x. So this is the special case of integration by parts. So let u equal to e to the x, therefore du is equal to e to the x dx. And dv is equal to cosine of x dx, and v is equal to sine of x. For the purpose of this problem, I'm going to let the integral equal to capital I. I will use this capital I a little bit later. Right. But for now, just so you know that the integral of e to the x cosine of x dx is equal to I, capital I. It's just a placeholder that I need a little bit later. So for this particular integration by parts, the answer is, or I is equal to u times v, so e to the x times sine of x, minus the integral of e to the x times sine of x dx. Right, so e to the x times sine of x, once again, this is exponential functions times trigonometry function, but this is a special case of e to the x times sine or cosine functions. So you have to do integration by parts again, right? So you let u equal to e to the x. So you notice that at first I let u equal to e to the x. Now I still let u equal to e to the x. And dv equal to sine of x dx. The antiderivative of that is v equal to negative cosine of x. So the capital I integral becomes e to the x times sine of x minus the integral, right? So uv, which is minus e to the x times cosine of x, minus the integral of negative cosine of x times e to the x dx. So you have e to the x times sine of x. I'm going to simplify everything now. So negative, so still here, negative e to the x times cosine of x. So negative here with negative here become positive. A positive integral of cosine, or rather e to the x times cosine of x dx. And I am distributing the negative sign in front of the brackets. So capital I e to the x times sine of x plus e to the x times cosine of x minus the integral of e to the x times cosine of x dx. Remember at the beginning, I say that, okay, I'm going to put the placeholder for the integral of e to the x cosine of x dx as capital I, right? So I'm going down here. I see my answer so far. I have I, capital I on the left-hand side, and also this integral, right? Integral of e to the x cosine of x dx. This is also equal to capital I. Now, instead of writing the integral, I'm going to write capital I equal to e to the x times sine of x plus e to the x times cosine of x minus capital I. So I combine like terms, right? So I get I, so I'm going to move negative I to the from the right hand side to the left hand side, and I get 2 capital I equal to e to the x times sine of x plus e to the x times cosine of x. And to complete the problem, I divided both sides for 2. I get capital I equal to 1/2 e to the x times sine of x plus 1/2 e to the x times cosine of x. And then magically put the plus constancy at the end because this is the indefinite integral. So in a way, this particular problem gives us the idea of we have to run in a circle in order to get the evaluation of the integral e to the x times cosine of x. Right? The similar procedure should apply to e to the x times sine of x. Right? Should be able to do that. So note here. So the same procedure can be applied to evaluate the integral of the form e to the x times sine of x. And the next part is the integration by parts for definite integral. So integration by parts for definite integral. So the formula should be the same, very much the same. Except now you have limit of integrations. The definite integral from a to b of u dv is equal to u times v, evaluate at ab, minus the integral from a to b of v du. So very similar to what we had earlier. Let's do one quick example. We evaluate the integral from 0 to pi over 2 of x sine of x dx. So x is the algebraic functions and sine of x is the trigonometry function. So you let u equal to x. Therefore, du equal to dx and dv equal to sine of x dx, or v is equal to negative cosine of x. Okay, so the answer is negative x times cosine of x, evaluate at 0 in pi over 2, minus the integral from 0 to pi over 2 of negative cosine of x dx. And therefore, you evaluate negative pi over 2 times cosine of pi over 2 plus 0 times cosine of 0 plus the integral from 0 to pi over 2 times cosine of x dx. Like cosine of pi over 2 is 0, right? So the first term here is 0. 0 times cosine of 0 should give you 0. And you're left with just the integral from 0 to pi over 2 of cosine of x dx. And the antiderivative of cosine is sine of x. Evaluate at 0 and pi over 2. So you have sine of pi over 2 minus sine of 0. And sine of pi over 2 is 1. And sine of 0 is 0. So this is equal to 1 for the answer. Right, so example. Can you evaluate this integral from 1 to e of ln of x over x squared dx? Alright, so don't jump directly into the problem. Think about this problem a little bit. Right, so remember, when we talk about this integration by parts and also integration by substitutions, it's always safe to let u equal to ln of x, right? But what about divided by x squared? Actually, you can rewrite this particular integrand as the multiplications between ln of x and x to the negative 2. So first, what you can do is rewrite this integral instead of fractions. You write as the multiplications ln of x times x to the negative 2 dx. So you see that using isolate, right? For L is logarithmic function. So in this case, Ln of x, and x to the negative 2 is the algebraic function. Right? So you let u equal to Ln of x. Therefore, du is equal to 1 over x dx. And dv is equal to x to the negative 2 dx. Right, when you set dv equal to x to the negative 2 dx, that means you want to find the antiderivative. So v is equal to x to the negative 2 plus 1 divided by negative 2 plus 1. Have x to the negative 1 divided by negative 1, or this is negative 1 over x. So by integration by parts, the integral becomes, by integration by parts, right, so u times v, which is negative 1 over x times ln of x, evaluate at 1 in e, minus the integral from 1 to e of v du times negative x times 1 over x dx. So for the first terms right here, I'm going to evaluate that, right? Negative 1 over e times ln of e minus 1 over 1 times ln of 1 plus integral from 1 to e of 1 over x squared dx. Why is plus? Because I have negative outside here and negative inside, so I combine them together to have positive term. So continue evaluate. So 1 over e, ln of e is equal to 1, and ln of 1 is equal to 0. So for the first term, I obtain negative 1 over e. Now for the second term, or the integral, I rewrite 1 over x squared as x to the negative 2 dx. Right, so it's easier for me to evaluate the integral. So this give me negative 1 over e plus x to the negative 2 plus 1 divided by negative 2 plus 1, evaluate at 1 in e. Negative 1 in e plus, this is going to be x to negative 1 over negative 1, or this is negative 1 over e minus 1 over x, evaluate at 1 in e. Right, eventually altogether you have 2 over e plus 1.